Hi everyone and welcome back to our YouTube channel. In this lecture, I will show you how to compute the determinant of a given square matrix by using elementary row operations. But before doing so, let's again start with simple examples to make some key observations again. So, here is the thing. For the sake of simplicity, I choose the size of the matrices of size 2 by 2. Say I have a matrix 1, 2, and 3, 9. So this is a 2 by 2 matrix, right? So say this is A. Okay. Let A be this given matrix. Okay, and another matrix, let's give another matrix like B is equal to 3, 9, and 1, 2. And we know how to compute the determinant of a 2 by 2 matrix. It is easy, right? Then what would we do? So determinant A is equal to 1 times 9. So we multiply the main diagonal elements and subtract this value from the non-main diagonal elements, right? So the multiplication actually from the multiplication of non-main diagonal elements, which is 2 times 3. So 9 minus 6 is equal to 3. And how about the determinant of P? So to find the determinant of matrix P, we do the same thing. So 3 times 2 minus 1 times 9. So 6 minus 9 is equal to minus 3. So the simple observation we make here, if you notice that we have 3 here, and we have minus 3 here. And what is the reason for that? So actually, if you notice, determinant A is equal to minus determinant B. If you notice, we have 1, 2, and 3, 9 for matrix A. But if we swap the rows, in other words, if we interchange these rows, and first row becomes the second and second row becomes the first row, then by performing this elementary row operations we obtained a matrix whose determinant is the negative value of the other matrix. So if the determinant of matrix A is equal to 3, then the determinant of matrix P is equal to minus 3. So we just multiply the determinant by minus 1. So this is a very important observation. So if we interchange two rows, then we have an opposite sign of determinant. So if one is positive, then the other would be negative, or vice versa. All right. This is one simple observation. Just keep in mind. And let's continue with another one. Now, say we take another matrix, namely C, and C is equal to, let's say, 1, 2, and 9, 27. So what is the difference between the matrix A and matrix C? If you notice that their first row is the same, 1, 2, but the second row of the matrix C is multiplied by the real value 3, so by the scalar value 3. So then what is the determinant? Let's see what is the determinant, or how is determinant affected by this situation. So again, we have a 2 by 2 matrix. It is easy to compute the determinant in the case of 2 by 2. That's why I choose the size 2 by 2. So 1 times 27 minus 2 times 9. 27 minus 18. Now we have 9. So the determinant of matrix C is equal to 9. So if you notice, guys, I just multiply one of the rows of A by a scalar 3, and the determinant, if you see that, moves from 3 to 9, so by the same magnitude. You see, it was 3, but multiplying the second row by 3, then determinant also is increased 3 times more than the first one. So it was 3 and now it's 3 times 3, so it's 9 now. So multiplying a row by a scalar has an impact on the value of determinant in the same way. So if you multiply any of the rows by some scalar, then actually this means that we multiply the determinant by the same scalar. So in magnitude, it increased in the same amount. How about matrix C? Say we are given another matrix T, and let the matrix T be, alright, let's give some name to matrix T. Okay, now say this is 1, 2, and say this is 5 and 13. Now how about this matrix? Okay, we are doing these examples on the matrices of size 2 by 2, but we can generalize this idea. This would also work on any size of matrix while trying to compute the determinants. Okay, now what is the determinant? Let's determine what the determinant would be for matrix T. So the same again, 1 times 13 minus 2 times 5, and then 13 minus 10 will yield us 3. And one thing you notice that it is the same determinant. But what is the difference between the matrix A and D? So what I have done in matrix T is actually I replaced the second row of matrix A by second row plus 2 times first row. So I performed the third elementary row operation in matrix T. Well, in other words, to obtain the matrix D, I performed the third elementary row operation on matrix A. And if you notice, it has not changed the value of determinant. So this is a very important observation. And how about matrix C? So for the matrix C case, what I have done is, again, to obtain matrix C, I performed the second elementary row operation on matrix A, and what I have done is I replaced row 2 by 3 times row 2, and multiplying row 2 by 3 will change the result of determinant in the same magnitude. So the original determinant was 3 for matrix A, but now we have the determinant value 9, which is 3 times 3. So the scalar has an effect on the value of determinant. So the second elementary row operation actually has an impact on the determinant value. How about the first one? How did I obtain the matrix P? Well, I performed the first elementary row operation on matrix A to obtain matrix P. And what I have done is I just replaced row 1 by row 2. And this is the first elementary row operation, as we all know. And what is the effect of this elementary row operation? It changed the sign, right? So we actually performed one row operation and we multiplied the determinant by -1. Alright, now, having said all of this and making these observations, now let's generalize our idea, because this lecture's topic is how we can compute the determinant using elementary row operations. And as we all know, by performing an elementary row operation, actually if we use these elementary row operations to find the determinant, then we are given a square matrix which is of size n by n, and by performing elementary row operations we reduce this matrix to another matrix, say B. Okay, And in the end, we have the matrix P, which is actually either the row echelon form or reduced row echelon form of the matrix A. And to do so, in other words, to convert matrix A into B, then we are allowed to perform three types of elementary row operations, and type 1 actually is what? Type 1 is swapping any row by another row. Okay, so we can replace one row by another one. And what is the effect of this elementary row operation on the value of determinant? Well, so here is the relation, as we all noticed in the above example. If we say the determinant B, well, which is the determinant of the final matrix, is equal to minus determinant A. But before proceeding, just I want to make one point very clear. So if we have only one row swapping operation, if we have two row swapping operations, then we multiply determinant A by 2 minus 1. So it means minus 1 times minus 1, which is again plus 1. So no change. So in other words, if we have even number of row swapping operations, no change on the determinant. But if we have an odd number of row exchange operations, then we multiply the determinant by minus 1. So this is the impact of elementary row operations of type 1. But as I said, if I have, for instance, 3 row exchange, then it means minus 1 times minus 1 times minus 1 and again minus 1, because we have an odd number of minus 1 multiplied by each other. Alright, and we have type 2 operation. And what is that? So here's type 2. So type 2 is, as we all know, we can replace row Ri by row I multiplied by some scalar namely lambda. Lambda is any real value, right? So what is the effect? So the effect is, if we perform this elementary row operation, then the determinant B is equal to, so the determinant B is equal to lambda times determinant A. So actually determinant A is what we are looking for. So in order to find the value of determinant A, we divide both sides by lambda, and lambda is the actually scalar that we multiply the row while replacing it by itself. Okay, and again, if we perform many type 2 operations, for instance, say I replace row 1 by, say, alpha 1 row 1, and if I replace row 2 something like alpha 2 row 2, then what would be the effect? So actually in this case determinant B is actually equal to alpha 1 times alpha 2 times determinant A. So how many different scalars are multiplied? We just follow them. In other words, we keep track of the number of elementary row operations that we have performed in the meanwhile, while at the same time trying to reduce our original matrix into the row echelon or reduced row echelon form. And another type is type 3, but as we all saw above in the example, type 3 operation doesn't have an impact. So if we replace row I by row I plus lambda times row J, then there will be no change on the determinant. So the final determinant would be equal to the original determinant. So determinant B is determinant A. If we only apply, in other words, this comes down to saying that if we only perform type 3 operations during the elimination process, then the determinant of our final matrix would be equal to the determinant of the original matrix. But if we have performed type 1 or type 2 operations during this elimination process, then we need to also keep track of the numbers of this type of operations and how many times did we perform. And we count them and take into account to compute the original determinant. Alright, having all said, now let's give an example. Let's give an example to understand what I mean by it. Okay, here's the example. Now, suppose that our matrix is given in this form. So say 0, 1, 3, 1, 2, 4, 0, 0, 3. Now let's find the determinant of this matrix by using elementary row operations. Okay. And the first thing to do, well, this is not in the row echelon form. And the first thing, as we all know, well, we can start by replacing row 1 by row 2, right? Because the leading entry in the first row must be a non-zero element. So the best way to start this elimination process is to replace the first row by the second row. Okay, now we have 1, 2, 4, 0, 1, 3, and 0, 0, 3. And again, while eliminating our matrix, in other words, while reducing our original matrix to that of row echelon form, we also keep track of the number of elementary row operations of type 1 and type 2. If we only perform type 3 operations, then there would be no problem. But here, as you noticed, we performed a type 1 operation. And what is the contribution of this type of operation? Well, in the end, I need to multiply my determinant by -1. But this is the first occurrence of type 1 operation. So if we have one more, then that means -1 times -1, and it is equal to +1. And multiplying by +1 wouldn't change the result. So if you have an even number of these type 1 operations, then there would be no effect on the amount of on the actual value of the determinant. But if you have an odd number of type 1 operations, then we multiply the original determinant by -1. Let's continue. Okay, now the second operation. What can I do here? All right, let's see. We can, if I want to reduce this matrix into reduced row echelon form, for instance, well, actually I don't need to do. Well, in this case, I already have obtained what I want, right? I can stop here. So I don't need to continue. If you notice, I already have an upper triangular matrix, right? Because below the main diagonal entries, all the values are equal to 0. And if we have an upper triangular matrix, it is easy to find the determinant value, right? So what is the determinant? So the determinant is 3. How would I understand that? The only thing I need to do, I just need to, well, I just need to multiply the elements that lie on the main diagonals. So it is 1 times 3, and it's equal to 3. Okay. So, but what I have found is, I found the determinant of matrix B, our final matrix, right? This is, if we call this matrix B, okay, and this is the determinant of B, which is equal to 3. However, as I said, we have one type 1 operation. So the determinant of our original matrix, which is the determinant of A, is decided by multiplying the determinant of B by -1. So -1 times 3 is equal to -3. So it is as simple as that. But by the way, if I want to continue, guys, I can continue. So now I have a row echelon form. But if I want to continue and turn this matrix into reduced row echelon form, I can continue to this process, to this elimination process. That doesn't change the value of determinant at all. But just the computational effort, that we put into this process would increase, right? So there is no need to do so. All right. Now, so since I perform an operation like this, then I need to take it into account. And if I want to here multiply this matrix by a scalar, then I need to take it into account as well. But if I only perform type 3 operations during this elimination process, then there is no need to do so. Okay. Let's give another example. So now, suppose we are given a matrix like this: 1, 2, 4, -2, 1, 3, 3, 1, 2. Okay. Suppose this is the matrix, okay? And find the determinant by using elementary row operations. Okay, say this is matrix A, okay, and find the determinant of matrix A by using elementary row operations. And if we want to make things easier, if we can only apply the third type of operations, then everything would be easy, right? So I will stick with this philosophy actually. So let's solve it. And the first thing I do is, what can I do here? So I can replace row 2 and row 3 by something else. For instance, I can replace row 2 by row 2 plus 2 times row 1, and row 3, I can replace row 3 by row 3 plus -3 times row 1. And in this way, what I found here, let's see what we get. So the first row is the same, 1, 2, 4, but the second and third row would be changed. So 0, 5, 11, 0, -5, and -10. Okay, now I check to see whether or not I obtain a row echelon form, but not yet, because Here's the leading entry. You see, we don't have a strictly increasing number of zeros. So we have one more zero in the last row. Okay, let's continue to the elimination process. We need to replace row 3 by something else. And this something else is replace row 3 by row 3 plus row 2. Okay, when I add row 2 to row 3, then I'm done. Okay, let's see what we have. So we have 1, 2, 4, and we have 0, 5, 11, and we have 0, 0, and 1. Alright guys, now look at this matrix that I obtained in the end. So I have an upper triangular matrix, right? This is a row echelon form. And I am done with the elimination process. And since I have an upper triangular matrix, as we all know from the previous lecture, to compute the determinant of this final matrix, I need to only multiply the main diagonal entries, which is equal to 1 times 5 times 1, and this is equal to 5. And this is the determinant of the matrix A as well. Why is that? Because if we again examine the type of elementary row operations that we have performed, is if you notice that this is the third type, this is the third type, and again this is the third type. So the type 3 operations wouldn't change the determinant at all. So our final determinant, which is the determinant of matrix P, say this is the B, right, the row echelon form, would be equal to the determinant A, that is our matrix given in the first place. And if you see, and as you see, actually it is a very simple process. Since we are all familiar with the elementary row operations, then it would be very easy for us to compute the determinant of a given square matrix by performing this elementary row operations. What we need to do is just keep track of the type of elementary row operations we have performed and count the number of them, and then see what we have in the final, and then compute the determinant of the final matrix, which is an upper triangular one. And all we need to do is just multiply the main diagonal entries and find the determinant. And then, depending on the type of elementary row operations, then take into account this recipe, right? So how many type 1 operations or how many type 2 operations we have performed. If none of them is occurred, then we are done. Our final determinant is the determinant that we are looking for. Alright guys, and that's it for this course. I hope you enjoyed that, and in this lecture we have learned another method to compute the determinant. Now we know how to compute the determinant of a given square matrix by using its definition, and also we know how to compute the determinant of a given square matrix by performing elementary row operations as well. And see you in the next lecture.